All right, so we're going to look at the model selection part 2. And to do that, we are going to be looking at regularization methods. When the sample size is bigger than the number of independent variables, the sheer volume of clean data will drown the random noise. This happens in linear regression. In linear regression, the features are completely independent. One of the assumptions of linear regression is that there must be no multicollinearity, or there must be no high multicollinearity. Then dependent noise. The noise is also purely white noise, purely random. Now, if you violate the assumption of no high multicollinearity, or if you violate the assumption about the sample size should be strictly bigger than the features. If you violate that, then there's going to be massive sample size assumption violated, and the OLS will suffer. The OLS will be blue, will no longer be blue. Guys, I just want to put on record that today's lecture is difficult. So you want to pay greatest attention. Stop whatever you are doing out there and put your very best, and I mean your very best, in concentrating and taking note. Else you will lose a chunk of important things. I want to set that on record now so that you pay attention, because you have to understand to even ask questions, and that is important. All right. Now, if the number of independent variables are more or even closely equal to the sample size, you will have a problem of overfitting. Okay. And so these are some of the problems we encounter. But then the problem is going to be a big problem, because when these things are there, the OLS variable, the independent variable, each independent variable has got a beta parameter, which later become the coefficient. The coefficient can be inflated big, and that is a problem. And you will see very soon why that is a problem. Now, in the normal OLS, we minimize the error sum of squares, or the residual sum of squares. And this is the residual sum of squares that we tend to minimize. Okay. Now, the residual sum of squares is given by the actual versus the predicted squared. You take the sum of that. When you expand this, you get this. This is what we minimize. So the whole thing is an optimization problem. But the optimization problem is fully unconstrained. There's no limitation. There's no constraint. The algorithm is to minimize all the errors. Listen to the point. All the errors at all cost. Now, why would you want to minimize all the errors at all cost? Well, at the cost of something. Like any linear programming, there is no non-negativity constraint. There is no bounds. You got to go all in. And the fact that there is no bounds means that the model is going to be unbounded. Now, when you have a normal linear programming, if you've done linear programming before, one of the assumptions is that the decision variables should be non-negative. But OLS is saying that there shouldn't be any non-negative decision variable. Everything, the weight, everything has to be found, and the weight can be as big as possible. So there is no limitation on the weight. It can also be negative. That is why in OLS regression, the independent variable can be very big negative and very big positive. But then in linear programming, you have to set a limit as to the independent variable, as to the decision variables, how big they can be. So one of the things is that the x's, the x1, and then the x2 in linear programming must be non-negative. But here in regression, we have not set that bound. And that means that the OLS is free to assign any large positive value or any large negative value to it. As long as those wild numbers cancel out each other to lower the training error, OLS will take them. That is good, but that is bad. So let's take an example to demonstrate the point I just said. So here you have, in fact, this thing has to be changed. I don't know why. Let me see if I can change it here. You have a regression model that has been estimated, okay? You have a regression model that has been estimated. And it says that their exam score is affected by a couple of things. Your exam score is affected by the hours you spend studying from a textbook. The hours you spend studying from a textbook. The hours you spend studying from a textbook, as well as the hours you spend studying from online lecture notes. So here you are, and you have to handle these situations. So you have the online lecture notes, and then you have the textbook. These are the coefficients. These are the errors. Take note that the coefficient divided by the standard error equals to the t statistic. And when you read the t statistic on the table, you're going to get the p-value. Okay, now watch this. If you check carefully here, what do you think? And I'm asking a general question because your answers will help you to understand. What do you think is the relationship between the hours you study and your exams? I'm talking about the hours studying from a textbook and your exam. What do you think? The relationship, should it be positive or negative? It is when you answer that I'll move slow. Should it be positive or negative? And when you know the answer, it's important that you are answering. You are raising your hand to answer. Stella.
Doc, please, I think it's negative.
It's wrong. Now, when the relationship, Christina, and I ask you why.
Doc, I think it's positive because when the more you study, the more you get better understanding of the content of what you are studying, and during exam you can be able to relate and transfer your knowledge into the question.
I didn't talk about study. I talked about specific kind of study, studying from specific books. David.
Yeah, Prof, it's positive because just by the table there, you have the exam score and the textbook hours.
Don't use the table. I'm giving you a general a priori knowledge. Don't use the table yet because the table is going to tell us something different. Richard.
So the more time you spend studying from a textbook, the more likely you are to do well in your exams. So the correlation is positive.
What about
the relationship is positive?
What about reading your online lecture notes? Go ahead, Richard.
It says it's still the same positive relationship.
Why?
The more time you spend studying your lecture notes, there's a likelihood that some of the questions will be based on exam notes.
Okay. So that one too has a positive relationship. So what do you see in the results of the table now? Does that reflect what you had in mind? Stella?
No, but it does not give the true relationship.
Why?
Because it's showing here that the textbook hours is negative, that compared in relation to studies, as in doing well in your exams. If you spend more hours in a textbook, it's negative. It gives a negative correlation.
All right. That's fine. Now, when we estimated these two independent variables on the dependent variable, the R square is 1. Is that good news or bad news? The R square is 1. Is that good or bad? You see, you're afraid to say the right answer, even though you know what the answer is.
Good.
Who's talking that is not raising the hand? Because you are not, you're afraid to show your hand. Also, you have to say the answer quickly, so you are not known. And still you will claim that you said it. You are talking about hand raising. Yes, Penel.
Yeah, please, I think it's good because the model is trying to say that all variations in the dependent variables are being explained fully by the independent variables.
All right, Dr. Say.
Yeah, good afternoon, Doc. Yeah, it is good. And as Pinel said, the closer your R square is close, the rate at which your R square is closer to 1, that makes it better. So once it's 1, that means it's good.
Yeah, that is the original idea, but it's wrong. And you're going to see that very soon. You see, it's the fact that R square is perfect. So what this one is saying is that you don't need to add any variable. You don't need to add any variable to this model to determine your exam score. The only thing that is determining your exam score is the notes you have and that of the online lecture notes. Is that the case? Okay, so there are issues, but R square is still 100%. Okay, the other thing is that you see that the beta parameters are large. So what this one is saying is that 1% change in studying is estimated to shift exam grade by an absurd value of 20%, 20 points. So it's positive for the textbook and it's negative for the notes, as you can see. But that shows that there's collinearity. The coefficients are inflating dramatically to counter each other. You see, they are inflating to counter each other. So this one says that your exam score is going to increase. This one says your exam score is going to fall. There's a problem. How can they not support each other? Because the points align perfectly to the specific plane. The standard errors will shrink. And you can see that it's very, very low. They are almost zero. If you check the standard error, they are almost zero. And you didn't see it, but when you go and check the confidence interval, they are very extreme. In fact, you can see that here with the t statistic. Look at how big the t statistics are. They are all having E plus 14, which means there are 14 numbers following the 2. That is in trillions also. There's a problem. So if you go and check the p-values and the p-values are all significant, that is wrong, misleading p-values. And so we are falling into the trap of overfitting already. Pay attention. Now, for you to see how problematic this thing is, let's say that a student studies for 5 hours using online notes, okay? 5 hours using this online notes, 20. So the coefficient now is going to be 20. We are going to use that to predict. So what will be the textbook? Textbook will be equal to the exam score. The exam score is going to be equal to the coefficient, and the coefficient is 5 plus, because we are not focusing on textbook hours, we are focusing on only note hours. And note hours, so it's going to be plus 20. Oh, sorry. Online notes. No. It's not using online notes. They are using textbook rather. Okay. They are using textbook. I need to make that perfectly clear. Not online notes, but textbook. So a student studies for 5 hours using only textbook. Okay. Using only textbook. What is going to happen here? If they are using only textbook, you have to use a textbook coefficient, isn't it? Only the textbook coefficient. So the textbook coefficient here is negative 19. So you multiply the negative 19 by 5. That will give you 20. Are you guys with me? If you are with me, say yes, so that I know. If not, say no.
Yes, sir.
Yes, sir.
Yes, sir. We have
Yes, sir.
Yes, sir.
So what happens is that now we are going to find out that when you increase your textbook hours, your exam score is going to reduce by 90%. Just think about that. So you're telling me that with all the textbook that I use, statistical learning, I'm going to reduce my it doesn't make practical sense. It doesn't. There's a problem. So for prediction, you come to realize that, ouch, the thing is truly a problem. So we need to find a way around it. Now, the best subsets that we did, the forward selection, the backward selection, all of them, they were trying to address the predictors. And seeing how the model changed as a result of that, in order to determine which of the set produces the best predictive power. So those ones here, this method that we looked at the last time, that's what they do. They want to, which predictors are the best? Now, instead of trying to do that, you could have easily just put all the predictors in the model, but modify the error function, in such a way that the coefficients that are not helpful are pushed to 0. My point is that some of the coefficients are not helpful. And if they are not helpful, move those coefficients to 0. So if an independent variable is useless, it's bogus, it's insignificant, then the coefficient of that must go down towards 0. Because the only way that independent variable must be insignificant is when the coefficient is 0. Instead of you having a very big one, okay, the coefficient is big, like this, and yet, this thing is not helpful in prediction. How? What method can help us to push the coefficient towards 0? What method? It's called shrinkage or regularization method in machine learning. Very powerful method. We are going to look at both of them. But before we look at them, let's try and understand the problem, inside the OLS. OLS has two problems. One problem is overfitting. The other is underfitting. Overfitting is bad. Overfitting is trying to memorize the exam question and then the answers. Not memorize. I mean, you take a past question rather, and then you memorize the past question. And then you also have the answer to the past question. So you also memorize the answer. If you go to the exam room and that same thing has happened, what do you think you're likely to get? Quick one. Anybody? If that same question has appeared, what do you think you're likely to get? Stella?
100%.
Now, if you go and that question, those questions that you have, some of them came and some of them didn't come, what are you likely to get? Or let's say 50% came, 50% didn't come. What are you likely to get? George?
50%.
George, I can't hear you.
50%.
He sounds very far. Wallace?
50%, sir.
Okay, now, if you go and none of those exact questions have come. Are you actually going to fail? Let's be clear. Are you actually going to fail? Stella,
Yes, Prof. You fail.
you may not necessarily fail. Stephen,
Yes, you may not necessarily feel because there are other factors that could affect.
oh, if you don't tell me those other factors, then what you said doesn't hold water. Ofori? Amina?
So you may not necessarily feel because there could be questions that have the same question
Structure.
similar to what you solved. Yes. Similar
Exactly.
to what you solved.
Exactly. So overfitting is not all that bad. Underfitting is worse. In this exam case, what is underfitting? Not learning. That is it. Not learning. Or learning very slightly. That's underfitting. So underfitting happens when the model neither performs on the train set nor the test set. Now, this happens in regression. These problems, they happen in regression. But then when you take the regularization or the shrinkage method I'm about to show you, the idea is to avoid this overfitting of the data. Now, why? Because if you understand, overfitting occurs when the number of the predictors are more or there are too many. Even if they are not more than the sample size, there are too many. And therefore, once you apply the shrinkage or regularization method, because of that, you see, when there's overfitting, overfitting can bring about a large difference between the training set and then the test set, their performances. So if you check the R square for the training set and you check the R square for the test set, you will see a big difference. That means overfitting is there. That's overfitting there. But when you have regularization, the number of the features that are used to train is kept constant. You don't change the features. But what overfitting is doing, what regularization is doing, is that the magnitude of the coefficient, the betas are reduced. I told you the idea is to, if the independent variable is not important, reduce the coefficient to 0, making that, but it doesn't ever get to 0, but at least the idea is to move it towards 0. And there are two most powerful shrinkage or regularization methods that are available. One is the the L2 regularization, and the other is a lasso, the L1 regularization. And we're going to look at them. Pay attention. They are not that simple, so pay attention to understand them. First of all, the two of them, the subset selection method we did last time, that one when we calculated it, if you go and check, all of them were using OLS, the normal least squares OLS, to fit the linear model. But instead of fitting the model containing some or a subset of the predictors, you are now fitting the model containing all the predictors. And what you are doing is that you are regularizing, you are constraining, you are shrinking the coefficient. When I say shrinking the coefficient, if the coefficient is 20, like the one we saw before, or negative 19, you are bringing them towards 0. That's the meaning of shrinking. I'll ask you this towards the end. Now, is that going to be helpful if you start shrinking them? Yeah, it may not be obvious from the start, but it turns out that this shrinking process will reduce the variance. Because at the end of the day, if the R square for your test and training set are similar, that's good. If your MSC for the test and then for the MSC for the test data and for the training data is similar, it's also good. So, what exactly is range regression and lasso regression doing? What they are doing is a range regression will introduce, and lasso regression will also introduce another terminology. Apart from the normal equation, they will introduce something called shrinkage penalty. Write it down. Shrinkage penalty. Shrinkage penalty. Now, how does it do that? Range will introduce a square of the beta value. So you remember that the normal regression will have a beta. Okay, range regression will bring about beta square. And then lasso regression will bring the absolute value of beta instead of the beta square. So that is how so what they are doing is that they are introducing another terminology into the model. Is that good? Well, let's see. Let's see whether this introduction is good. So this is our usual regression model. The residual sum of squares. This is how we know it. This residual sum of squares that you see here, guys, the idea is to minimize this error sum of squares with the intention of getting beta parameters. And then you can now fit it into the model perfectly to get an estimated value. Now, range regression will shrink these estimated coefficients. You see this one here? Range is going to shrink it towards 0 by changing the entire regression sum of squares. So instead of minimizing the regression sum of squares alone, it will add the shrinkage penalty. This is what I mean by to add the shrinkage penalty. So it's not only taking the RSS, but it's adding the shrinkage penalty to it. And so you got to now minimize all of them, both the RSS, the residual sum of squares, as well as the shrinkage penalty. Remember, the beta has been squared, so that's already. But then there's something else. You see that there is a lambda. When we go to the software doesn't call the lambda, it calls it alpha. So take note. What is that? What is that lambda? What is that alpha? Now, match it. If you remove the summation sign, this lambda or this hyperparameter tuning, you call it the tuning parameter. This one is being multiplied by the beta parameter. Take note. So you have something multiplied. You see that thing, that's what is going to shrink the beta. The entire set, the entire information here. This one will multiply this and they will bring it down or take it up. Well, in this case, you are bringing it down towards 0. If you're in the negative world, you are bringing it down towards 0. If you're in the positive world, you are bringing it down towards 0. What is this alpha or lambda? It tells you the amount of shrinkage to be applied. It has to be determined somewhere in addition to the coefficient. You are finding that one separately. So the new loss function that you see under the RSS, under the range regression, the new loss function, the new regression sum of residual sum of squares is made up of the RSS plus the shrinkage penalty. The shrinkage penalty is going to encourage choosing all coefficients other than the beta naught, because the beta naught is not important. All the coefficient by shrinking these betas towards the origin, towards the 0. Because anytime, let me draw something. Anytime you are shrinking something towards a 0, that means you are moving towards the origin. That is what this range regression is doing. Now, like the OLS, the range regression is trying to find that in the data, is trying to find that that estimate that will fit the data properly. And it does that by minimizing the residual sum of squares. But this second term is the most important thing. This one is that shrinkage penalty. Now note that the shrinkage penalty is made up of two things here. The first one is what is known as the tuning parameter. The tuning parameter. The second one is the usual beta parameter. The idea is we need to make this beta parameter small towards zero, but we don't want it to get to zero, so that the effect of shrinking the estimate towards zero is felt. Now, why would you want to shrink some of the betas towards zero? It will help you in variable selection. It will help you to know which variables are good and which variables are useless, because there are so many useless variables. See, if you understand this thing, you can use this one to determine useless things among useful things. So the tuning parameter, that's the most important word there. The tuning parameter, it serves to control the relative effect of the two terms in the regression coefficient estimate. It will regulate how the overall will work. As for the beta, they won't work on their own. We need to regulate them. That means that if the beta is big, if the lambda is big, and the lambda is the same as alpha in the software, if the lambda is very big, you're going to pay more for having large coefficient. So you have to perform, you have to prefer the coefficient closer to zero than those far away from zero. That is when lambda is big. When lambda is small, you're going to see that we are going back towards OLS. You're going back towards OLS. So selecting a very good lambda, a very good tuning parameter is critical. And one thing we can use to do that, and we shall do that also in the software, is using cross-validation. Cross-validation can help you to be able to do this. So when lambda is equal to zero, what does that mean? Let me go back here. I've said this many times. When lambda is equal to zero, what does that mean? When lambda is equal to zero, what does that mean? Anybody? When lambda is equal to zero, if you check this equation, you will understand. When lambda is equal to zero, what does that mean? Yes, George.
The penalty has no effect.
Yeah, but what does that mean? Where have we got into at that stage? Where have we got into? Which world are we in now? Somebody should tell me. We are sitting in a certain world. Yes, Nanaya.
Said the model behaves exactly like the standard OLS.
Standard air.
OLS.
Judge.
Yeah, so it goes back to the traditional OLS.
Good. Keep that in mind. I mean, I've said it millions of times. I didn't know it was going to delay you like that. Okay. So we are back to the OLS. When lambda is equal to zero, everything here will fall apart. We are left with the residual sum of squares. Now, when lambda is equal to infinity, what it means is that the beta parameter is going to go very big. Very, very big. And what is the problem with that when it goes very big? Well, it means that all of the ridge regression coefficient estimates are going to be 0. Because if it is going big, okay, it means that the coefficients are all going to go down, 0. So we want it to be between 0 and infinity, respectively. I mean, exclusively. That's why you should take note. We should want it to be between 0 and infinity, excluding 0 and infinity. So the kind of lambda you choose is important. That's the point. That's the whole point. A different kind of lambda will lead to a different kind of beta. Therefore, whereas OLS will just tell you one set of betas, okay, shrinkage methods will give you a whole family of solutions, different beta values, because of different lambda values you have. Okay. So let's go back here now to our analysis. Now that we are, let me edit this one again. Now that we are in the exam zone, so we are going back to the exam zone. Remember, we had a table for the notes, okay, textbook, online notes. And then we had another one. What was the other one? We had textbook hours for learning textbook and hours for learning online notes. Now, I wanted to check it carefully. These are the alphas or the lambdas. When the lambda is 0, like we said, we are back to OLS. Take a note. And so we don't want that. Now, why don't you want that? We can see that the note information is what? Is negative and it's big. And look at the R square. We saw that the R square is what? 100%. Now, that is highly unstable. Unstable because it is already predicting negative exam scores. So we now move the alpha from 0, which is OLS, to 1. Now check what is happening here. You can see that the intercept time starts rising. The textbooks start falling because we are shrinking them towards 0. Then the coefficients start falling. We are shrinking them towards 0. The R square starts falling as well. It was 100% here. God not be doing that. And then we increase the alpha penalty even more. From 1, we move it to 10, it starts falling further. We get to moderate coefficients shrinking. Then we go to 50. And you can see that the coefficient, I mean, the intercept is gone up again. And then the textbook coefficient is coming down. And then the notes is also coming down. This is powerful. We are now in the stable negative coefficient, almost 0 zone. Then you increase it to 100. So this is all rage. Everything I've done is rage, just that this is the stoppage. So with rage, you can see that the signs are what? Positive, both of them. Not only one of them, both signs are positive. Alpha equals to 100 means that the lambda is now equal to 100. So the model begins to align itself with reality. The textbook was having what? Positive. The online was having negative, and now the online is having positive 0.09. And all of these are very useful behaviors that increase a student's score. It makes sense. It makes sense. What about prediction? Well, let's now introduce that same new student who was now only using the online note. You remember that student failed Porto. He didn't just fail, he had a negative 90. Now let's bring that same person, multiply it by the coefficient. Watch something carefully. Something has changed here. You see that the equation coefficient is no longer 5, but it is what? It is 17.54. That is this one here. And then we note that the textbook coefficient is 1. But then we said that this student is not doing anything with textbook. He's only doing everything with online notes. So textbook was what? 0. An online note, he's spending 5 hours on online notes. And the coefficient there tells you that the 5 that she is, if you multiply it by 0, you get 17.99. 17.99. Is that a good predictor? Absolutely. So it's this reflects reality. So you can see that now the lasso that led to the ridge that led to the optimum answer is a ridge with an R score of 93.88 and a ridge with a beta parameter for textbook as 1 and for the others as 0.09. This is beautiful. If this is not beautiful, we have now moved away from the -90 to a +17 for a prediction. This is beautiful. If it's not beautiful, I don't know what you've eaten. Let's move on. So range regression is fantastic, but it has a problem. It has some, but it's very fantastic. Let's look at some of the beautiful things. It makes it more expensive. The hyperparameter tuning. The tuning parameter, makes it more expensive for the model to simply choose whatever coefficient you want. And this will in turn prevent it from overfitting the data. So it is good when there's a possibility of overfitting. That's one thing. That tuning parameter is wonderful because it doesn't allow it to go and select a particular coefficient just like that. But it has a problem. It has a problem. When you are increasing the lambda or the alpha, okay, as you raise the lambda or the alpha, the freedom to choose the coefficient, because now as you are raising it, you see, previous one that we just had, we were raising it all right, but then you can see that you have to now know it's between the 1, the 10, the 50, and the 100. Which one is the best? Well, we saw that 100 is the best, but question is that it could be that the 100 is not the best. So that's what we are looking at, because the lambda will increase. Now, the lambda is going to increase. You always will start with the 0 lambda or no lambda. And the lambda is going to increase. And then you now are limited. Because when the lambda is increasing, the variance is also increasing, isn't it? You remember the lambda is to bring the variance, increase the gap between the test scores and then the training state. So the variance is coming down. And what do you think we'll have to do with the bias? The bias will increase. The bias will start increasing. So that is a challenge. So you need to find a sweet spot. Where is that sweet spot? So what you do now is that if you check this is the MSE, guys. This is the mean squared error. And here, the lambda is moving from left to right. The lambda is moving from left to right. The squared bias is this black one. The squared bias is this black one. And you can see that as the squared bias is going upward, the variance is coming downward, the green. The variance is coming down. So, but you want a level that is sweet spot for both of them. This is the whole point of model selection. You want a sweet spot. And that sweet spot is when the bias, the squared bias, and the variance are intersecting. That happens to be the minimum point of the MSE. Take note. That happens to be the minimum point of the MSE. So the minimum point of the MSE will guide you to selecting that sweet spot. This sweet spot is the only thing that can help us to know that our method is fantastic. And it is, ladies and gentlemen, fantastic. So that's range regression. The disadvantage is that OLS, listen carefully here, this is important. OLS, when you are estimating it, the predictors don't care about the unit of measurement. You can use anything. For example, if some of the variables are in gallons, some of them are in kilograms, some of them are in trillions, the unit of measurement doesn't matter as far as OLS is concerned. So we say that OLS is scale equivariant. OLS is scale equivariant. But in the shrinkage methods, the shrinkage method like range regression, before you use it, you got to make sure that it is scale equivariant, but it's not. So what do? You standardize the predictors. And you use this formula to standardize the predictors. You see, you standardize predictors means that those that are in millions, those that are in billions, those that are in trillions, you are bringing all of them to be at par with those that are in tens and ones. You are standardized. Regression doesn't care about that. Automatically, it sorts it, but lasso regression cares. So you got to go back there and make sure that all the variables, the independent variables, are standardized. I didn't say the dependent variable. I said the independent. They are the ones going to fight with each other. They are standardized. And when all the independent variables are standardized, guys, something is going to happen. Now you can go ahead and use range regression. That's it. You can use range regression. So we said that OLS is scale equivariant. The features of the large scale get small betas. That's OLS. And then the features with small scale get large betas. So this is very important. So sometimes you estimate some things and then you come to realize that when you look at the data set shows that this GDP is in billions. But then when you come to the regression coefficient, you see that the coefficient calls it 0.011. Oh, coefficient is 0.011. Why? Because it is so big, what is happening is that regression has actually made the interpretation smaller. Because at the end of the day, you got to go and multiply that 0.0111 with the big value, the trillions, so that it becomes a bit more billion or a bit more million. That is it. The range regressions don't do that. They are scale blind. See the word? They are scale blind. Okay. So naturally, what the range is going to now do is to crash the large data by destroying the model in the presence of the features with different measurement, unless you have what? You have scaled the data. If you have scaled the data, then range regression has no problem with you. Therefore, it is always best to standardize the predictors before you use range regression. I think it's clear. So so technically, if you solve this standardization issue in range regression, then you don't have a wahala. But all the same, there is another wahala. The wahala is that, unlike the subset selection method, range regression takes all the independent variables. It will include everything. Everything will be included. Why? Because the goal is to shrink the coefficients towards zero, even though never zero. So we are trying to simplify the model in the sense of reducing the number of predictors. Okay. And that is the whole idea. You are reducing the number of predictors. Okay, range regression says that if you want to reduce the number of predictors, I will shrink the coefficient down for you. Okay, I will shrink the coefficient down for you. And so it will include all of the independent variables. But if some of the independent variables are bad, they are included. So that is range. Let's go to lasso. Who can tell me the full meaning of lasso? What is the full meaning of lasso regression? Stella.
Least absolute shrinkage and selection operator.
You think that this answer you gave, everybody doesn't know? They all know. They know. But sometimes when they are opening their mouth to answer, they don't. They know. Okay, lasso is also called a penalized regression. A penalized regression. Remember that it also has a penalty function. You remember that a shrinkage penalty. Okay. So look at its shrinkage penalty is this one. Okay. It's just like the other one. What is the difference between the lasso penalty and the ridge penalty? You can tell me. Who remembers? What is the difference between the lasso penalty and the ridge penalty? What is the difference? And get your Jupyter notebook ready, opened. Amina.
I think the lasso has the squared and the ridge has the squared and lasso has the absolute.
Okay. So what this lasso is doing is a small change has a big effect on what the estimated coefficient should look like. Small change has big effect. Small change has big effect. Now, the lasso is sometimes called L1 regularization, and the ridge is L2 regularization. Now, like the ridge, the lasso is also, the lambda in the lasso is set to 0. So the lasso, whenever it is set to 0, it becomes the OLS regression. And then as it increases, the coefficient estimates will shrink towards 0. When it is very large, the coefficient will become 0. Now, please note, when the lambda or the tuning parameter is large, ridge regression will not become 0. It will be closer to 0. But when it is extremely large, ridge will still never become 0. It will be close to 0. But lasso will become 0. Take note. Lasso forces you to the limit when you realize that the coefficient, when the lambda, the tuning parameter is large. Okay. So why does it do that? Because it is trying to tell you that the thing is useless. And so once the thing is not there, it's better. It's better that it's not there than it is there. And that is what lasso is doing. It's better that it's not there than it is there. Any question? Any question? All right. And also, it shrinks it to 0 so that we don't have any multicollinearity problem. It shrinks it to 0 so we don't have any multicollinearity issue. All right. Lasso also shrinks the coefficient towards 0, but like I said, if it is big, if the tuning parameter is very large, it will force it to 0. But in the case of lasso, it has the effect of forcing some of the coefficient to be exactly equal to 0 when the hyperparameter is large. Okay. So there's one thing we did with the best subset selection. The lasso is just performing a variable selection. So if beta is large, if beta is 0, we know that the whole of this will be 0. Okay, so this one becomes useless. That is why we say that the lasso will give you more sparsity. In other words, the models that involve only a portion of the variables. Take note, lasso gives you more sparsity than ridge regression. All right, but the key point is about that tuning parameter, that lambda, that alpha. That lambda is important to know how to get the best lambda. That will also give you the sweet spot, if you can remember, that we spoke about. Let's turn to that lambda carefully. Lambda can help you, but we need to know which lambda gives you the best. Because the lambda is from 1 all the way to infinity. Not even 1. It's anything 0 and above. So it is 0.0001 up to infinity. Lambda is big. So we need the best method that will help us to get the best lambda. And boy, oh boy, the best method is cross-validation. You remember cross-validation? It gives you a simple way to get the best lambda. Why? How? This is how. You got to choose a grade, like a set of the lambda values. Then you will calculate a cross-validation error for each of the lambda values you've selected. So suppose you select between lambda 1 up to lambda 100. You are now going to find the cross-validation error rate for each one of these lambdas. Then you select the tuning parameter or the lambda which gives you the lowest cross-validation error. Write that one somewhere. Pick the lambda that gives you the lowest cross-validation error. And after that, the model is refit again using all of the available observations. And then watch the word, using all of the available observation. At first, you were using cross-validated, but now using all of the available observations. And then you select the value, or the hyperparameter tuning value. You select that one. That gave you the lowest cross-validation error. So it's very important that you know that this whole thing helps. So when you check this one, in all of this, this is a cross-validation error. It is, as lambda is going up, the cross-validation error is coming down and then rising up. So you don't know which one to use. But the one that you will use, come here. Okay, the same thing here, but this one we are dealing with the coefficient. The one that you are going to use is the one that gives you a lower coefficient value. Not a lower, but a reasonable coefficient value. So cross-validation error are here. This one here. Now watch this. This is error. And normally error, you want the smallest one. Okay. So here, when you trace it to the left, it matches the low. So this point here will tell you the proper lambda to use. So the lambda here is the one that is the winner because it is giving you the lowest cross-validation error. That's the point. The lowest cross-validation error. Somebody says, can we get a minute to take it all in? All right. So should I give you a minute? Should I give you like 3 minutes to soak it in?
Yes.
Yes, Doc, we'll be grateful.
Let's quickly get that. Up to this point, what have you learned so far? What is the difference between, why do we need the cross-validation error? Who can tell me? Why do we need the cross-validation errors? What is it for? What is the essence of the cross-validation errors? And remember that normally these cross-validation errors are many. Why do we need them? Because they are going to help us to select the best error.
Yes.
And the best error is the error that is the what? The best error is that error that is the what? Judge.
The least.
The least, that's it. That is the least. Now, we indicated that the tuning parameter which is lambda, but also called alpha. This tuning parameter, what is it doing? What is its job? What is the role of the tuning parameter in this regularization method? What is it doing? This lambda, what is the role? What is the role of the tuning parameter? What is the role of that lambda? The coefficient tells us by how much the independent affect the dependent. Now, the lambda or the tuning parameter, that by how much, it controls that by how much. If it affects the dependent variable by more or by less, because you said by how much, by more or by less, that is what a tuning parameter, the lambda, is doing. We know that the independent variable are going to influence the dependent variable. We know, but by how much? The beta parameters tells us that by how much. But then the coefficient, these beta parameters are the coefficient. But then how they affect is also being influenced by this tuning parameter. So the tuning parameter is more or less affecting the way the coefficient of the independent variable is affecting the dependent variable. This is important. So you should know the role of beta and you should know the role of the lambda. It's very important. It's very important. So now we're going to take the data set and you should open the data set, which is the haters data set. This data set is what we are going to use to explain and understand everything about the shrinkage method. If there is time, I will discuss data leakage as well. So let's go back to the data set. You should all open yours if you have it. You all have it. I'll put it on the page. And to start with, I want us to understand what this data is all about first, before we start using it for this regularization. We are going to run three major models. The first is the OLS regression. The second is the range regression. The third is the lasso regression. But within the range regression, there will be a lot of tuning parameters being used. Okay, and a lot of cross-validation errors being calculated. The same thing with the lasso. I need somebody to slowly read the story, because if I start showing you this thing, you won't understand until you understand the story of the data set. So tell us the story of the data set. Who can do this reading for us? Who can do the reading?
What should I read?
Yeah.
Towards regularized regressions. The HITES dataset is one of the most widely used datasets in statistics, machine learning, and predictive analytics. It is particularly famous for demonstrating multiple linear regression, ridge regression, lasso regression, principal component regression, partial least squares, subset selection, and model regularization. The dataset was popularized by the textbook An Introduction to Statistical Learning. Background of the dataset. Imagine you are a data scientist working for a Major League Baseball franchise. Your manager asks, "Can we predict how much salary a player deserves based on his past performance?" Instead of relying on intuition or scouting reports, you decide to use historical performance statistics to build a predictive model. This is exactly the problem the HITES dataset addresses. Business problem. The objective is to predict player salary using historical baseball performance statistics. Although the context is sports, the modeling techniques are directly applicable to business problems such as predicting customer spending, predicting employee salaries, predicting loan amounts, predicting company profits, predicting transport costs, and predicting demand. Source: the data contains statistics for Major League Baseball players from the 1986 season, along with their 1987 salaries. Thus, performance during 1986 is used to predict salary in 1987. Original data set is 322 observations, 20 variables. After removing missing salaries, 263 observations. After removing missing salaries, 263 observations. Variable: salary at bats, then hits, role,
All right. So
response.
that's okay because that one is talking about the variables. So the
Okay.
main variable of interest, guys, is the salary of a player. That is an annual salary of the Major League Football player, that particular player, for the 1987 season. That's a target variable. And that's the one that we are going to predict using the player performance statistics. And the performance statistics are, so it's like you are trying to, that's why they normally say that a player like Ronaldo was expensive at the time because they have calculated the number of passes, the number of goals, the number of this, runs, and all of that the player has done. Okay. And this, because you are a business analyst, this side here talks about the business interpretation of each variable. So as an example, this is baseball, by the way. So if you take hits like this, hits is the number of successful hits that player made during the 86 season, not the 87 we are looking at, the 86 season. So you're using the past data. And then the number of home runs that player actually did during the season, this current season. And then also RBI, the runs batted in, the number of teammates who scored as a result of this player's batting. So it's like if it was in a normal football, it would have been like the passes you give towards somebody, assist, the final assist before the goal was scored. So all of these are factors, okay? They all are factors that determine, okay, the salaries. And the defensive errors that a player has made, the number of defensive errors committed by a player during the season. So all of this will determine the salary that player is going to get. Guys, are you with me? Are you following? You need to understand the data.
Yes, sir.
The original work didn't have this data interpretation, so I've given you. Now, we are ready to run. There are some codes that you should know. They have to be standard. The first one is the standard scalar. You remember we said we'll be doing scaling, and that if you don't do the scaling in a range regression, don't start. Don't start. So we need a standard scalar. We also need the train test split. And here you're going to see that we'll do a 50-50 test split to start with. Then we'll also be doing a number of cross validations. So we have to import a cross validation score. And then we'll do the cross validation itself for both range. The range cross validation we'll do, the lasso cross validation we'll do. And then we'll be calculating the mean squared error to determine the fitness or the performance of each model. So this will load the data and show the first 3 rows. Let me edit the first 3 rows and show the first 10 rows. All right, so you should do the same thing. Oh, by the way, these variables are dummies. Okay, league. So if you go up and check league and division, this is league. The league is either the player is in the American League or the player is in the National League. So the league in which the player competed, so it's a dummy variable. And because it's a dummy variable, it was originally A and N. So we want to code them as 0 or 1. Okay. So that's it. Then division. Division 2, we had divisions such as the East Coast Division and the West Coast Division. They were dummies. And so we had to code them as 0, 1. And finally, the new league. The new league the person has joined, the league in which the player played during the following season. Okay, so that one too is there. So all of these 3 dummies, we have to indicate that. So we code the dummies and add the dummies to the original data and show the first 10 rows. I'm doing that. And that's what you have here. So you can see that the last columns, they are the dummies. Okay, they are the dummies. Remember, they are 2 levels, 2 levels, 2 levels, 2 levels. 2 levels like true or false, east and west, and things like that. So that is what you see there. Remember that some of the variables are 0. Okay, doesn't matter. They are still variables. All right. So that's a data set. Okay. Who has been able to run the data set just as I've done? And it is showing, different from the one that the 3 that was showing. Who has done that? If you are following me, it changes your thought process. You see mistakes in yours, which are not in mine. So take note. All right. Next, we are going to look at the information about data. So when you run this, it will tell you about the information, all the necessary, those that are integers, those that are floats, and all of that. You see them all here. Now let's come to the big deal. In this big deal, we want to define the dependent variable and then dependent variable. The dependent variable is salary. Okay. The independent variable is everything except salary. That's why we use the word drop. Everything except salary. This code is going to split the data. Watch it. We are splitting the data into test and training test, a training set. Now, which test size did we use? And what does that mean? Which test size did we use? And what does that mean? Which particular test size did we use? And what does that mean? Yes, Stella.
Doc, please, I'm seeing that the test size is 0.5. That's 50% of the entire data set. So we split it into 2 ballparks.
All right, that's fine. That's fine. So we are using test size of 50%, 50% for the training set, 50% for the test set. And please remember that it includes both the dependent and independent variables. Take note. It's both the X train and the Y train, X test and the Y test. Okay. Now, we go to the standard scalar. Okay, just a second. We go to the standard scalar. What is the standard scalar, by the way? So that's it. Please watch that. This is X train scaled. Do you realize that there is no white train scaled? Do you realize that there is no white train scaled? Do you see that? Who can tell me why? Who can tell me why? Why there is no white train scaled? Who can guess why? Yeah. There is no white train scale. Do you know why? Let me call on some of you. David Ama, are you here with us? Okay, so we standardize only the predictors. We don't standardize the response variable in a range regression. That's it. We don't standardize the response. We standardize only the independent variables and not the dependent. That is all we standardize. Okay, so you can see that here. So I'm now going to show the results for that. Okay, and now we go to the next one. The next one is the actual range regression. Now take note of something here. Where is this? Oh, the thing is, the thing is frozen. I don't know why. The thing is frozen. Okay, so let me show. So this is a standardized regression. Now, I don't know why I brought this first, because I'm supposed to bring this first. I can't believe this. All right, let me do this one first, because that's what I wanted to bring first. That's very strange. So after the standardization, I'm going to run the regression. I'm just swapping this. I'm going to run the regression with range regression with lambda equals to 0. Okay. That is, I just want to type that is back to OLS. So I'm just going to run the OLS regression. The OLS regression, if you check here, the OLS regression is when the range alpha is equal to 0. That's what I'm going to do. Watch the way it is. I write an equation called reg3. Okay. Doesn't matter the name, don't worry. And then I fit the train scaled. So if you check it, it's a train scaled. And then the original Y train. This is only on the training data, but then the scaled part of the training data for the independent variable. Then the predicted Y. I indicate that I want to get the predicted Y. And the predicted Y is coming from the model I just ran, predicting based on the test scores. Based on the test scores. Okay. You will now print the series, okay, to showcase the columns. So this is going to give you the coefficient of the results. We'll also print the mean squared error. Okay, and remember, this is on the test, not on the training. Okay, the test as well as the predicted. And then we'll now showcase the training score and then the test score. All of these are on the training data set as well as on the test data set. So let me run that. And this is what you get. This is like OLS. So if you had done the ordinary OLS regression, this is what you would have gotten. The AT bat would have given you negative 266. Some of these variables are heavily positive. For example, look at these two in the middle. One of them is negative 1,399. Whew, that is big number and also negative. And then the one just below it is big number and positive. Anyway, what is the value of the mean squared error here? The value of the mean squared error here is what? Who can tell me? What is the value of the mean squared error, Stella?
116,690.
Good. So that is 116,000. Okay, that's a lot of mean squared error there. And then the training score, okay, the range training score that you have there is 61% and 32%. So that is for the normal regression. Okay. Is that good or is not good? Well, the first thing that you will notice here is that you will notice that the variables coefficients are very big. Okay. Big, large betas that we spoke about is evident here. Okay. It's very, very evident. So that is the first issue that we are going to deal with. The second issue is the the mean squared error. We could have also shown the R squared. So we now start with what? An arbitrary regression model. Why do I say arbitrary? Arbitrary regression model because we are not going to select the tuning parameter, the alpha. Remember I told you that when we come to the software, it's not called lambda, it's called alpha. So I'm just choosing an arbitrary alpha, which is 4. So I'm going to run the range regression here. The same thing. I'm using the X train scaled and the Y train. The Y was not scaled. We estimate the Y predicted. We do the series for the coefficient. We do the MSC and then everything as before. Okay. But we are using for range reg 1, unlike range reg 3 that we did. This is going to estimate for the alpha. Now watch this. This is the answer. You see the values here. They have become a bit smaller than before. Remember those ones were big, but they are still negatives and positive big. Okay. But the values have come down. If you look at this AT bat is negative 210. If you go to the normal regression, it's negative 266. Hits in the regression was 197. Hits here is 193. It's still good, but it's still not too differentiated. So we need to check the R square. The MSE. The MSE is what? Is 102. Has it come down? Oh, it's gone up. Which one? Has it come down or gone up?
That's come down.
It's come
It
down.
has come down.
Okay. Now, we need to check the intercept because see, here it didn't have the intercept. So we can check the intercept. In fact, the previous one too, I can check the intercept. Let's go to the previous one. So the previous one, that is the OLS. I can run the intercept, call it reg 3. So let me just type reg 3 and just see the intercept for that. That is 532. Now let's look at the intercept for this. The intercept for this is 532. So you can see that the intercept is constant in both ways. Okay. But then I told you that what we just chose, it was arbitrary. Remember? I told you that we just chose an arbitrary value, which means that we just felt like we should select something and we just did. Okay. Now, the previous one, the MSE was 116. Is that correct? That's it, 116. Okay, that is for the OLS one. What does that mean? What does that mean? 116. Remember that the errors are squared. And because the errors are squared, the MSE is measured in the square of the response variable. Normally, it's best to use the root MSE. Let me just mention that. Normally, it's best to use the root MSE and also add the R squared to it. But we're in a hurry. We just want to showcase some things. Okay. So if you look at the training score is 61 here, and then the test score is 32. Okay. The difference between these two is what? Who can tell me the difference? Let me see. Here, the difference between this is about 20.287 thereabout. Check it. Okay. So what it means is that the model is performing what? Better on the training. Okay, if you check it, this is 61%. It's performing better, substantially better on the training data than on the testing data. And you have that gap, the gap of about 20 something, which shows that the model does not generalize well on the unseen data. That's what it means. The model does not generalize well on the unseen data, which means that it has learned patterns in the training data that don't necessarily transfer effectively to the test. And this is a typical example of overfitting. Although the regularization method is going to provide, a solution to that. But the key point is that there is overfitting in this regression model. So let's go to the regularized one. Okay. The regularized one, do you see that the gap has closed a bit? By how much? The previous one, the gap is about 28. Oh, I hope you guys are following me. Okay. The MSE has reduced, but then when you look at the training and this, you see that the gap has closed a bit. It's about 17 now. So what can we say? That the overfitting is reduced by a bit. Okay. The overfitting is reduced by a bit. So it just goes to show that the regularization method that we just chose is good. But the point is that the regularization method we chose is arbitrary. So let's go and choose a proper one. Let's generate an array of alphas because the alpha we chose was 4. So let's generate an array of alpha values ranging from very big to very small, essentially covering the full range of the scenarios. So we'll set up this one. That give me a bit of alphas here. I want you to give me a bit of alphas ranging from 0.1. 0.1 is a start, okay, and stopping by 100, and then stop before 0.01. Okay. So this is going to produce approximately 100 values of alpha. Okay. I'm not going to show all of them, but I'm just going to give you, I'm just going to let it produce the best. Okay. So what is the best here? Let's calculate it. Okay. That is it. So you get 72. 72.57. So we see that the value of the alpha that resulted in the smallest, and by the way, it's a cross-validation in case you didn't see. This is a ridge CV. So ridge cross-validation. That resulted in the smallest ridge cross-validation error is 72.58. And it's producing so that's the one that is producing the lowest error. Okay, so we're going to select that. So what is the name we give to it? We called it ridge CV.alpha_. So when we come here in our next model, we are going to put in that. See, ridge CV.alpha_. That's what we're going to use that. And then everything is as before. And then we run this again. Let's see the result. Now, what do you see about the coefficient now? You can tell me. And what do you see about the MSE? And what do you see about the train and test score? I need comment from you. What do you see about the coefficients? Let me call some people. Yes, panel.
Coefficients are reducing. The mean square error has also reduced. And the gap between the train score and the test, the train and the test, the gap is closing up, which means that we are reducing the overfitting in the data.
Okay. What else have you also spotted? What else have you also spotted? So there are four major things that are here. Yes, Amina.
I was going to say that the MSE has also increased
Oh, increased?
or reduced.
Hey, my dear, it's in front of you. So if you say or,
It has reduced from 1,100 and something to 900.
Oh, okay, has reduced. I've forgotten the.
you've forgotten, my dear. You should have checked first. Okay. So clearly you can see that the MSC is now below 100,000. All of them were above 100,000. Now it is below. But what is even more beautiful is that the original OLS, if you can remember, the original OLS, the gap between the training score and the test score was 28. Then when we chose alpha equals to 4, okay, if you can remember, when we chose alpha equals to 4, something happened. It brought it down to 17 gap. Now, what is a gap? Approximately, how many is a gap now? Who can tell us? How many is a gap now?
Like 0.08.
Oh, yes. So approximately 0.08. Okay, which is like, in terms of percentage, it's like 8%. So from 28% down to 17%, down to 8%. Fantastic. Okay. Now tell me, which is the largest positive coefficient and which is the largest negative coefficient? Largest positive coefficient and largest negative coefficient coming.
The largest positive is put out, which has 84.94. And the largest negative coefficient is division _W, which is negative 46.6.
Very good. Excellent. Very good. Now, notice also that none of the coefficients are exactly 0. Do you see that? Yeah. We normally expect this because ridge regression shrinks the coefficient towards 0, but it doesn't perform the variable selection. Take note. Every predictor remains in the model. Even though some of them becomes very small, they are still inside the model. So none of the coefficient is 0. And those that are very, very big, they contribute positively to the predicted salary. That's what it means. And those that are negatively big also, they do a similar one like that. Okay, so now we have 51% for the training. We have 48.9% for the, what do you call it? 42.2% for the other one. And this is all due to the variables that were not included in the model, okay, at hand. So what is our final comparisons? What will be a final statement? What we can say is that in this very cross-validated model, the ridge regression demonstrates moderate predictive performance here. It explains about 51% of the variability in the training data, 42% of the variability in the test data set. The relatively small drop in the R square, and you can see that is about 8.9 percentage points. That shows that the model generalizes reasonably well. It's not severely overfitted. It's not severely overfitted. And when you look at the coefficients, okay, they show that, like you said, put out, walks, career, home runs. That is a CHM run. And then the career RBIS, the CRBI. And the hits, all of them have the strongest positive contributors towards salary. But when you look at division W, okay, you notice that division W has the strongest negative association, you know, and you can see that all the predictors are expected in the model. So we can actually look at all of this from that angle. We are now ready to use the lasso. I don't know whether I've not even spoken about the lasso, but the lasso is here. Let me see whether we can quickly go to the slides. Okay, so this is a slide. I've talked about all this. And all these points have been made as well here. So just as we said, it looks like the ridge regression improves over the regular least squares. Now the lasso. So before we begin the lasso, take note that we saw that the ridge regression with the wise choice of alpha can do some great things. Okay, the ridge regression. And you can see that we selected some particular alpha values. In fact, when it comes to the credit data set, I'll let you do it by yourself. Okay, the credit data set. I'll let you do it, that one by yourself. So take notes. Okay. So the question is, and it can outperform the least squares as well as the null model on the hitters. We now ask whether the lasso can give us a more accurate, more interpretable model than the ridge regression. So all of this code, we are going to just run them and see what is going to happen. We're going to run this. Then we will now perform a 10-fold cross-validation to choose the best alpha for the lasso as well, and then compute the associated errors. We will now use the best error to fit the lasso regression, and then we will see the outcome of that. So let's go. So this is it. So this is a lasso. We are using an alpha value of 10. Okay, that is arbitrary choice or no. Okay, and that is what you see. What is a quick observation you see regarding the lasso? Who can spot that? The quick observation you see regarding the lasso. Look at the results all the way from here up to here. What is a quick observation? Stella.
It allows the zero values.
It what? You say it's what?
I easily noticed that the lasso method allowed zero values in the coefficients.
Very good. That is the first, quickest observation here. What else do you see? Making it good or bad, what else do you see? What else do you see? Now, what do you see about the R square? The R square value is 50. The R square is 54.33%. Okay, for the training. And then 40%. How many gap? If our primary objective at this stage was prediction, we would have chosen the ridge over the lasso. If the objective is identifying the most significant predictors whilst maintaining the parsimony, then lasso would have been the best to select. Okay, because lasso is very good with sparsity. We spoke about that. So, but that was 10 arbitrary choice. So let's go to where you select not just 10, but you choose a range. You select the best alpha. So here, the best alpha is 26. Remember that when we're doing for the lasso, the best alpha was 72 something. Okay. And you can the best alpha 26 gives us this. Okay. This scores. And this is a cross-validation approach that we are using. So let's use that best alpha, this one. Okay, this one. Let's use this best lasso alpha to now go ahead and then do our analysis. And now there's a final work. What do you see again? It wasn't too bad from our arbitrary choice, was it? It wasn't too bad from the arbitrary choice. It wasn't. So you can see clearly. And again, when you check, you will see that the range regression is still winning, generally speaking. Okay. But then the lasso has done what we said it was going to do. The coefficients are truly pushed to the point of 0. That's it. Okay. So we've been able to do all of that. Just go through the one for the credit data set. Do the one for the credit data set, and then you'll be able to get the key information. So this is the one for the credit data set. Go through that yourself and enjoy the process of all this we have done for the haters data. Do the same thing for the credit data set. It's just incredible when you go through. I'm just going to end by summarizing a point on data leakage. We have just discussed the need to standardize the data. We've discussed the need to split the data, perform cross-validation, feature selection, hyperparameter tuning. We've done that. We've done all of that. Do you see my PowerPoint?
Yes, Doc.
Okay.
Why is somebody saying he doesn't see? So all of them are very important. Very, very important. Because failure to follow the right order can lead to data leakage. Okay. So what is a correct machine learning pipeline to follow so that you don't have data leakage? First, let's understand what data leakage is. Data leakage happens when pre-processing, like standardization, normalization, one of them is done on the data before you split the data. If you could remember, we split the data first. Okay. We split the data into training and test sets first before you will do the standardization. If you don't, data will leak. Data will leak. Why is that a problem? Because if the test data has already adapted to the model before you even run the test, you're actually testing the model's ability to handle the real world. No, you're not. Okay. We are just testing how well it remembers a shared secret. So the moment you deploy a model, the new data won't share the secret. It won't be, it won't be adapted, and the model is going to flop. So step one, rule number one, split the data before pre-processing. Write it down. It's very important. Okay. I don't want to go through all of the rest. Split the data before pre-processing. And then pre-processing must always be fit only on the training data. Only on the training data you do the pre-processing. Okay. This is not negotiable. And then the repeated pre-processing must always be fit only on the training data. So you can check the couple of the data leakages on this. Check the data leakages so that you know exactly how this is done. Okay, I've put the codes there, run the codes one by one, and then check the data leakages there. So let me do a summary of everything. 1 second. Model selection. All these things that we've done is model selection methods. Yeah. Model selection methods are a very important tool for data analysis, especially when you are dealing with big data sets that involve many predictors. If you do a research into all of this, you will get sparsity. And when you get sparsity, that is where lasso regression comes in. That's it for today, ladies and gentlemen. That brings us to the end of the entire caboodle.